Hello and welcome everyone. I'm your host Stefan Burns, geologist, geophysicist, space weather guy, here to report on a convergence of asteroids upon Earth's orbit. We've had a bunch of close flybys by asteroids just in the past week. It's not like we never see this, but this is quite anomalous. Now, I reported on this first 2 days ago when we had 3 asteroid flybys back to back to back in 4 days, all closer than the Earth-Moon separation distance. At that time, I thought that was notable enough to report on, which I did. Now we have 8 asteroids passing closer than the Earth-Moon separation distance, which from when I've been tracking this, and I can show you the list that we have right here, when I've been tracking this and I've been looking at this for a long time, it's very rare to see this many dark orange boxes, which are the asteroids that have this flyby approach of less than the Earth-Moon separation distance. That's kind of a key figure. Now, none of these asteroids are going to be impacting Earth. As far as we know, we don't have any impact. So you see at the bottom of the list here, May 18th, we have a 21-meter diameter asteroid that will be passing 0.2 lunar distances. So these are close calls, but as far as I know, and just in general, I think if one of these was going to hit us, there would have been an alert. Instead, they've been calculated to pass close to the Earth, but not impact. But what this is showing us, and we'll look at the orbital data because I have it loaded up and we're going to explore around in the visualizer, and I'm going to explain effectively accretionary dynamics in the solar system, which is how the planets formed, or at least a very good model of and theory of explanation for that. Because what we're seeing here is effectively a condensation point in an asteroidal jet stream. And it converges right on Earth's orbit. And that's no coincidence. So the other thing to keep in mind as it relates to asteroids and these convergence points, which we call a jet stream, a la Hans Alvin and other space astrophysicists and more, is that you can have big objects within these as well. Now, the largest asteroids in this list here, we see that for specifically the dark orange, which is less than 1 lunar distance, the largest that we see here is in fact at the bottom with 2026 JH2 at 21 meters. So about 70 feet across, more like 65, 66 feet across. Big asteroid, okay? That's a big one. You don't really want that hitting the Earth. If it's 6 meters across, that's a big one. 3 meters across, that's big. 6 meters, those will hit the atmosphere and they're unlikely to actually impact the Earth, though fragments may rain down. But in terms of like an impact crater, probably not going to get that from 10 meters, 10, 15. Once you get to 20 meters, you know, there's a little bit more uncertainty. If you get to 40 meters, like you can get maybe not an impact on the ground in a crater, but air burst, huge areas where this massive wind shock and the TNT detonation effectively. So it's important to keep a close watch on this. And well, I guess it doesn't matter because we don't even have the technology to deflect it. We did do a mission called the DART mission where we hit an asteroid with a little probe to see if we could actually adjust its velocity and its orbit and everything, and it barely nudged it. You know, if some big thing was found coming in and we had 2 years heads up, maybe the space agencies of the world could get together and devise some sort of, you know, mission to deflect it with thrusters or to just detonate a huge nuke on it to deflect it, and hopefully that would solve the problem rather than creating like a fragment meteor storm. But we don't really have anything that we can do. So I don't know, maybe you shouldn't even be aware of this in the first place. Maybe ignorance is bliss, because if there was to be something bigger coming in at this moment in time, I would err on the side of government inefficiency and basically inaction rather than us actually doing something. Though I would like to hope that we could pull together. I think humanity at the base could do so, but whether the actual powers that are flying these rockets to space, and we haven't really developed our space program much. Now I'm getting a little off topic, but there's not really much that we could do should something big actually come in. So that's the thing. But we are seeing a very clear trend here over the past week now with these asteroids condensing down effectively to Earth's orbit, and many of them getting very, very close to the planet. And if we look at this list one more time, you'll notice another one here. This is 2026 JK2. It has its closest approach on the 15th at 1.2 lunar distances. So that's outside the Earth-Moon separation, but it's still very close. It has a diameter of 26 meters. So that's a big one. And the thing is that these orbits change over time. We'll explain that. So if you're new here, hello, welcome. I'm your host, Stefan Burns, and we cover what's happening with the Earth energetically. So we're looking at, for example, earthquakes, volcanic activity, geomagnetic storming, severe weather. We extend out also and look at the sun, solar activity, space weather, big solar flares, coronal mass ejections. We do have a coronal hole that will be hitting us with its high-speed stream in just a couple days. So we have a G2 geomagnetic storm expected soon. So we cover these sort of factors. Also planetary alignments, planetary resonances. Right now we're in the midst of a superior conjunction with the planet Mercury. In fact, it is a Ceres, Mercury, Sun, Earth alignment. And we almost have the new moon in that alignment as well. So we do have a fairly notable interplanetary alignment right now, active today through the 15th. But really actually today through the 16th when the new moon happens. And we have some big sunspots that are raring to go. We haven't had big flares from many sunspots in a few days, but the possibility exists at any moment now, effectively, for us to enter into a radiation storm, for us to have a big solar flare and coronal mass ejection launch our way. There's 2 sunspots that could do this, respectively. So we cover all that. We also look into these planetary and interstellar cosmic factors and much more. We talk about consciousness and metaphysics and all this stuff. I'm just an interested, curious person, and I share everything that I learn with you, and I like to speculate a little bit, but I also like to get grounded every now and then with some good science. But, you know, we explore all the different domains. So if you like the sound of that, then please subscribe. So let us just simply talk about what's happening. And we'll probably do a question and answer too. So if you have a question, then make sure you save that for the Q&A section. I'll pull some questions from the general chat. Though if you want to ensure that your question is answered, you can attach it to a super thanks and I will answer that, because those questions, they get put into a different list. So you can ask them at any time during the stream and I will answer them after the main presentation. So thank you so much. Let's look at what the heck is happening here, okay? So here we have our orbit viewer provided by NASA JPL, and I wish I could shift this over laterally into this blank space here for you, but they lock the viewing, so I can't shift it over here. But we see these 10 objects. If we go here, I'll show you the objects I've added. So we have all these objects added. The only one I didn't add, and actually maybe this asteroid list will fit in nicely. Yeah, kind of. I can kind of put it like this. The only one I didn't add was 2026 J0 or JO right there. For some reason it wouldn't load, though it's loaded before for me when I was plugging it in. But instead I added 2026 JK2. So all the asteroids here are of the dark orange, let's call it, like that dark salmon color, except for J0, but I added in JK2 instead, which is still only at 0.2 lunar distances away from the Earth for its closest approach. But this one's notable because A, its diameter is 26 meters, B, its velocity is high. Here we have 20.5 kilometers per second for its velocity, whereas below, yeah, 21 meters across, but its velocity is half that. So this is actually, we have some clues in this data set right here illustrating very nicely these jet stream dynamics which exist. So let's start off by just zooming out and looking at these orbits, okay? So we have all the planets plotted out to Jupiter, and these are near-Earth asteroids, all right? So near-Earth asteroids are in this near-Earth environment. They're not in the normal asteroid belt, though they can overlap. We see some of these are going fairly far out there. And I have a video too of the asteroid belt, which I can show you. I have it somewhere. I loaded it up. Where is it? Maybe I add this video really quick. I know I added it, but I'm just not seeing it. So I'll just recreate it right now. But I kind of want to give you the broader scope first before we go more in depth. So I think it's important to establish that understanding. So here is a visualization of the asteroid belt. Thousands of objects, mainly concentrated 2.1 to 3.5 astronomical units, some of them 10, 50, 100 kilometers in diameter, but in general, most of these objects are quite small, and we don't have them all mapped. Here we have the visualization with all the known asteroids going up to 2018. And well, there's a lot more that we know of now because of these new all-sky surveys that are specifically looking for these objects. But you see how many of near-Earth asteroids exist. See all these like cyan colors? Those are near-Earth asteroids. So they are quite prevalent in our solar system environment. The thing to keep in mind is that, you know, their sizes can be 5 meters across, 10 meters, 50 meters, 2 meters, 12 meters. I mean, bigger too, right? Apophis 2029, that's very large, like very large. It's less than 1,000 meters across, but it's a big one. You don't want that, and that's getting closer than our geosynchronous satellites. But in general, space is huge. So it's not like these are, you know, all that close together most of the time. Most of the time, they're spread out. Again, we see that very clearly here. You see their orbits are all spread out. The thing is, though, is that if you zoom in, you notice that they all converge down to this point right here. And let me just click forward for you. Here we see them come in. Here is the Earth-Moon system. And we see the moon's orbit, right? So that's the Earth-Moon separation distance. A little bit of variation in that, but we'll just basically keep it at the average quantity of 1 lunar distance. If you go forward here, we see how all these asteroids are converging together, even though their orbits are actually quite a bit different. So there's something here to this. Now, you could make the argument that this is just observer bias, which is the fact that, hey, the fact that we all observed these because they got close to the Earth, of course, indicates that they're going to have this convergence in their orbits because, yeah, we noticed them. But there's plenty of times that we're zooming through space and we don't get these sort of convergences because, well, there's known physics that explains how these convergence points are formed. You can call them a jet stream. So we go forward, and I went a little too far forward here, but you'll see the Earth zooming through, the moon rotating around. You'll notice actually there's kind of a grouping here, and this really helps to explain the theory of jet stream accretion. So we first, and let's really zoom in. So here we first go, and I'm going to turn myself off so you can see this better, but I'm just going to step this forward one at a time. We see that 2026 J01 is the first one to come into our system. See how close it is? Okay. And then we go forward a bit more, and now we see 2026 JM2 crossing in really close to the Earth, just slightly above. Okay. Zoom out a little bit. So you see that we had 2 close crossings, pretty close together. You can see the date down here. It's the 8th of May for this moment in time. And then we go forward, and here's our next 2, or even our next 2. You see 2026 JU1 coming in like that. See that guy right there? And then you see 2026 JX1 coming in. That one sweeps by. So those two are kind of paired together. And then look at this. You have another pair. 2026 JF2 slicing pretty close to the Earth right here. And then you see 2026 JD1 swinging in closely. Now, if you go forward, you will see that we get 2026 JK2 to get close by, but that's the one that has a separation distance of 1.2. So it doesn't get within that Earth-Moon separation distance, but gets very, very close. Notice it has a high inclination, okay? JH2 there, having that higher velocity as well. If we look at that list again, JH2, or I think it's J, are we looking at JK2? Yeah, JK2 there, having that high inclination and high velocity, and then we go forward more, and here is JH2 getting very close at just 0.2 lunar distances away from the Earth on the 18th. Look how close this one gets. I mean, this is really wild. There's the Earth. There's this 20-meter asteroid flying right by, effectively. So this is a close call. It will not hit us, as far as we know. None of these will, but it pretty beautifully illustrates the concepts that I'm about to teach you as it relates to jet streams. And this is applicable to asteroids and meteorites and a whole bunch of even just dust grains in space, how they accumulate together. Because how did we even get to the planets in the first place? That's a big question of like, how did the planets even form? And the conventional models, which are still being used to this day, even though they are basically disproven 50 years ago, you know, science is stubborn. The conventional models don't really make sense, that you just have this cloud of gas that somehow gravity just pulls in. If you actually do the calculations, at least some astrophysicists have back in the day, and you know, you can still do them now. There's not enough force just inherently with a cloud of gas to form a complete contraction. And then also begs the question of how do you get this differentiation of the planets? The density distribution varies, and the orbit distances vary. And if you have, for example, Jupiter, maybe we go back to here, and we'll actually just look at Jupiter, for example. Here we have Jupiter. Well, you have Saturn over here, right? You have Mars right there. If you were to take all the gas located in a band going halfway out to Saturn and halfway to Mars, right? There's going to be a lot more gravitational force near the actual growing embryo versus the outside edge. And gravity is a very weak force. So you don't have the force simply to pull it in from the edge. So these models of gas collapse, obviously gravity is an important factor here, and there is some of that. But in terms of how that explains all the planets and their orbits and their properties and distributed densities across their orbits and the lack of density distributed across the asteroid belt, doesn't make sense. So these asteroidal, meteorite, and dust grain accretionary jet streams actually makes a lot of sense. And well, we're seeing evidence for it right now with this current transit of all these asteroids and this clear condensation point here. So we'll get back to this, but let's go through some of the data now and just kind of do an explanation of what happens. So when you have we'll just call them particles. When you have a large number of particles in Kepler orbits, there are two things that can happen. If there is an interaction, they can be elastic or inelastic. And of course, the sizes can vary, the velocities can vary between them, the relative velocities, and that really determines what happens. The material can vary. You can have an iron meteorite, a stony meteorite, right? All these factors exist, but in general, there is this cognitive bias that if something bumps to something else in space, that it is elastic and the two things will bounce off of each other and also fragment to some degree. And so, for example, there's a common belief that the asteroid belt is the exploded remains of a planet that formed in between Mars and Jupiter. But if you were to actually really seriously take that into consideration, well, the overall mass of the asteroid belt is like 1% that of the Earth's, which is also still far less than Mars. How is it that you have the inner planets being more massive, and then you have Jupiter being the most massive planet? Actually, the distributed density, if you were to take the mass of Jupiter and distribute it out across its orbit and do the same with the inner planets, their distributed densities are very similar, yet the asteroid belt is order of magnitudes lower because, again, it has such a low mass. So how do you have this planet explode, yet the distributed density is different? You're probably not going to have these things fling out beyond the solar system too much, because that requires a tremendous amount of energy, the sun being a huge gravity well. So there's a lot of holes in this idea, and there's no evidence for it. There's also a wide variety of chemical compositions with the asteroids and more. You have trans-Neptunian objects that have been deposited into the asteroid belt, interstellar objects, I'm sure. You have different types of asteroids. What we do see good evidence for is that you not only have elastic collisions that can be fragmentary, there's a fragmentation, and you would call this a positive diffusion, which is typically what's assumed. You actually have more often a negative diffusion. So when you have these things interact at whatever size and scale, it's all fractal. Whenever you have these things interact, they actually are more likely to be inelastic, and to, when they hit, maybe there's some fragmentation, but when they hit, to make their orbits more self-similar, and their eccentricity will go down. That's the ellipse of their orbit. They'll become more circular rather than oval. They're more likely to become self-similar. The inclinations are going to reduce. The inclination is cutting through the ecliptic plane. So it'll become more and more flat along the ecliptic plane where all the planets are. And their velocities will get lower and lower relative to each other. Eventually, if you have objects moving close together in space and the relative velocity is very low, now you have the ability for them to come together. And of course, this is over cosmic timescales, but over cosmic timescales with enough collisions, they can actually fuse together. And this is how you get accretion. Because how did you get the planets in the first place? You need accretion. So it's the theory is that you have plasma that is coming in from an interstellar source, this infalling gas, because there is some sort of central body where gravity has collapsed somehow. And there is this rotation magnetic field now. This is the idea proposed by Hans Alvin and others. Ionization, due to the critical velocity, this infalling gas accelerates, ionizes, now stops because electromagnetism is such a stronger force than gravity. It's able to hold back in this magnetic field. In certain plasma structures, you have, for example, perhaps in the past, like the far distant past, the hedogonic era for the formation of the solar system or other solar systems, right? You have these super prominences, these plasma conduits, these Birkeland currents that extend outwards. There, plasma can undergo effectively chemical differentiation. You have light elements and heavy elements separate out. You can get grains to form. Once you have grains, little dust grains and particles, you can get them to accumulate together, form slightly bigger pieces like meteorites, like little meteorite fragments. They can accumulate together into asteroids. Asteroids can accumulate together into a planetesimal, and now you get planetesimal accretion, and you can get a planet to form as these planetesimals start to go in. And the calculations that they ran, at least, show that there can be a runaway accretion fairly early on. It depends on the density that's distributed in that area of space, the plasma, all the different conditions, but some will form very quickly, others will form slower, and the asteroid belt in this model is a souvenir relic of the accretionary process that finished for the entire rest of the solar system, except in the orbit of the asteroid belt. and you could also speculate for the trans-Neptunian regions where you have a whole bunch of dwarf planets and comets and asteroids and more. So what happens, at least this is a really good idea, is that in these regions where dust accumulates, you get these jet streams that formed. And in the jet streams, because you have these objects coming into close connection with each other, they form bigger and bigger bodies. That embryo turns into a planet. And so again, it's effectively this dynamic where you have these objects over time, as they interact together, their orbits become more and more similar, and eventually they'll fuse into one object. You have the actual asteroid belt. 80% of the mass, evidence for this is that 80% of the mass of the asteroid belt is contained within one single planet. This is the dwarf planet Ceres. So you already have a huge amount of mass concentrated in a single asteroid. That's Ceres. And then you have the next three biggest asteroids containing a lot of that mass as well. And then the remainder, like let's say 5%, is distributed across all the others. So you see this in action. Ceres has been able to, over time, accumulate all this material because of jet stream formation and these collisions in general being inelastic. So you have Ceres, let's say 1,000 kilometers across. Let's go back in time, make it 500 kilometers across. You get a planetesimal to come in that's 20 kilometers across. Yeah, you're going to get some fragmentation and some stuff flown out, but in general, most of it will absorb into the main body. And, well, the dwarf planet Ceres gets a little bigger and bigger and bigger and bigger. So that is the idea. Now, with that in mind, let us go back to our look here at these orbits, and you'll see something interesting. We'll get our list back up too. You'll notice with our list that the objects that get the absolute closest here, JM2 right there at 0.1 lunar distance, and also JH2 at 0.2 lunar distances, their velocity isn't that high. Remember, this is their relative velocity to the Earth, right? So JM2 is only 5.8 kilometers per second, JH2 9.2. Now these are still fairly high values, but it's not 50 or 60 or anything like that. Now, the fastest object ever recorded is 3I Atlas, and that accelerated all the way up to 68 kilometers per second. Fastest ever. So the typical range is going to be 5 to 30 kilometers per second. And you'll notice that on this list here, the highest, I think, is actually this 20.5 for JK2. But the ones that are closest to Earth having lower velocity values makes sense because they got closest to that condensation region within the jet stream. They've probably gone through more of these inelastic collisions and therefore are further along in that condensation journey. More evidence. Here we can see, let's go back again and go forward as we saw. We see that these two, J01, JM2, very, very similar, right? Look at their orbits, very, very similar at that moment in time. At that location, they're coming very close together. Now, if you zoom out, their orbits there are differences, of course, across these orbits, but in general, they're actually kind of following a similar trajectory. So you see that how the orbits are condensing together. We're looking at this at like an intermediate stage. That's at least the idea. I can't say any of this definitively because, well, I wasn't around 4.54 whatever billion years ago. All right, but these are really good ideas, and we're seeing evidence supporting these theories right now. That's what we're examining. If we go forward again, see, we have two more coming in close together. They have these very similar orbits. Then look at these two, have very similar orbits right here. And then the one that has the orbit that's the least similar of these is the one with the highest inclination, right? Look at the inclination on, I think it's JK2 right there. We'll pull up the list again. It's the one that's coming at like 20.5 kilometers per second. It has the highest velocity, relative velocity, and it also has the highest inclination. And as these collisions occur, the orbits become less eccentric, so they become more circular, and their inclinations go down. So JK2 is probably, now the fact that it's 26 meters in diameter means that it's grown somehow to that size, but it's also coming in likely with less, maybe it's a newer member to this jet stream. You always have things moving around, by the way, and these orbits are not static. The moment you have a collision, orbits change. So there is this kind of thing I've noticed with people, and that space and the orbits of asteroids and comets and everything, it's like totally static. Like, oh, nothing ever changes. It's like, well, on the human time scale, perhaps that's kind of true, but there's actually a lot of evolution with these orbits. They're not static. It's not like this asteroid JK2 is going to be in that single orbit that we see here for the next billion years. It's going to shift and change and evolve, and it's going to grow or fragment apart. And again, there is in general more accretion than fragmentation because there is actually a lot of physical processes that promote accretion rather than fragmentation. When you have grains get close to another in space, if there's electrostatic forces involved, well, they can form these fluffy aggregates because, well, if they're charged and they stick together, yeah, it may not be like a mineral or molecular bond formed through some impact, heat, and then fusion and mixing the material like a shot glass or something like that, you can imagine, right? Melting of metal and everything. But you can get electrostatic forces to form. And if you have that form a fluffy aggregate to a large enough size, now you can actually start to get quite a bit of heat to get released during impact, which then can fuse two or more objects actually together in a pretty significant way. So this is how you move up. You have these electromagnetic forces and these gravitational forces working together in sequence. So this, as I see it, is a really beautiful example of jet stream accretion and process, and effectively what it means to get to it and really to get to the thumbnail, which says impact is coming, is that eventually there will be impacts, right? This is a jet stream accumulation point, and the whole point, like just physics, gets these things and puts them together. So impact's not coming tomorrow, hopefully, but eventually they will impact each other, and we will continue to get accretion of these near-Earth asteroids to Earth. Earth will continue to absorb these. And the question is just, well, will it, cause problems or not? Here, we showed this in the last video when there was just 3 of them. This is a asteroid simulator. And let's just choose a location, just kind of, well, yeah, we can just, here, this is the perfect location. The Eye of the Sahara, the Richat structure, okay? So if we just do a test run here, and I'll turn myself off so you can see behind me, because I see this asteroid launcher. We'll do a stone asteroid, and let's choose that upper limit that we had for the other one, which was 20 meters or so. So let's just call it 70 feet. And let's choose our Richat structure, launch our asteroid. We had an asteroid airburst. So blew up 13 miles above the ground, explosion equivalent to 345 kilotons of TNT. Impact this size occurs every 59 years. If we launch another one, this time though, let's bump it up to 200 feet with a stone asteroid and launch that guy. Let's see what happens. Airburst, 6 megatons of TNT, 500 years, 0.75 mile wide fireball. And yeah, you start to get some pretty severe damage to the ground there in terms of fires and shock waves and wind shock waves. So that is I think I chose a 200 foot stone asteroid. It'd be even more significant for an iron asteroid, of course, because it's denser, quite a bit stronger, as you can see. And if we even go to a denser material, for example, gold, they have this example here with gold. We'll keep the diameter same, speed, everything. This is just for kind of illustrative purposes. If you see that a gold asteroid, now it's making a crater, okay? So these impacts do happen. We see these craters on the surface. There's a rich history. Earth has a very dynamic past that has been quiet at times. It's also been cataclysmic at times. It's just what it is. This is how the Earth formed. This is how the Earth will continue to evolve to some degree due to these sort of asteroid and comet impacts. Now, something else I wanted to cover today is the fact that we have a superior conjunction of Mercury occurring right now. So let's give that a look because this is pretty cool. It's occurring right as we're here together in the live stream. So we can give this a look here. And this is Mercury coming in. This is our C2 coronagraph. So this is our close view of the sun. The sun is denoted by this white circle there. They put a disk over it so it blocks out the light of the sun so we can see the fainter light of the corona, the solar wind, these solar storms. You actually get a plasma filament to launch off on the far side right there. I checked the SUVI imagery and you can faintly see that there is a launch of plasma from the far side just before it appears in the coronagraph imagery. So that's not Earth directed. It's just from beyond the limb. But Mercury's coming in here, and the superior conjunction will be when Mercury is exactly in line with the Earth, and in fact, or the Sun, and well, the Earth on the other side. And you notice that Mercury, sometimes with these conjunctions, it's swinging in well above or below the ecliptic plane because Mercury has inclination to its orbit. All the different planets do, but Mercury is a bit more than most. So often it's way up above or below the ecliptic plane. This one is occurring right along the ecliptic plane. It's going to be passing through a perfect alignment with the Earth tomorrow. On the other side of Mercury and the Sun from us will be also the dwarf planet Ceres, which I mentioned in the asteroid belt. So we have this Ceres, Mercury, Sun, Earth alignment, and with the new moon coming just a day after this really goes exact, so that's the 16th of May, we have that moon almost in that alignment as well. So this is a powerful force, and I would think that the planets and their orbits and everything also influence the asteroids. I mean, we do know that for a fact. If we go here again, the Jupiter actually groups a lot of the asteroids together. You have these Trojan asteroids, which aren't shown here. I could pull it up. Maybe I find the slide for the Trojan asteroids. Let me see if I can pull it up. Because it's quite cool. We do know that, yeah, here we go. We do know that there is these stable populations of asteroids that hang out at these Lagrange points on either side of Jupiter because of Jupiter's gravity. So these are called Trojans. There's a few other populations as well, and there's this mixing of them. So as you can see, they're not distributed homogeneously across space, these asteroids. There is natural segregation and condensation of them at times. In the asteroid belt, it is quite chaotic, but as we just saw with these near-Earth asteroids, they're all flying super close to Earth. They do have these condensation points where their orbits cross each other very closely, and across, let's say, 10,000 orbits, which on a cosmic time scale is nothing, right? Let's say it's 2 years, 1 to 2 years, because these are near-Earth asteroids. So their orbit around the sun is similar. 1 to 2 years. You take 10,000, that's 20,000 years. 20,000 years, you for sure could get a collision between those guys, and actually multiple, and then you start to see out shifts. And we only plotted 8 of them, right? How many of them are out there that we don't know of? That's really the big thing. The amount of asteroids that we have no clue about is quite high. And if we're flying through a condensation jet stream, and we have evidence of these smaller ones because we found them, then that I would say is a sign that we're right now in a statistically riskier position for there to be a big impact. So do I think a big impact is about to occur? No. I think the risk is still overall, the absolute risk is still very low. Though something, again, we need to be very mindful of. We should be developing these programs actively to protect us, because when it comes in, when is, it's not if, it's when. When, though, could be 10,000 years from now. It could be 500 years. It could be tomorrow. Like, it could just be this sneaker asteroid that comes up from the sun direction. We didn't see it because the sun is so bright, and all of a sudden it's there on our doorstep. That'd be the worst case scenario. But these sort of jet stream condensation regions are where you're most likely to have an impact. And so we should be mapping these and keeping track of them. And the best way to find them is through observation. And well, we just found one effectively. That would be, that's what I would say. I would say that this is strong evidence that we've just found a jet stream condensation region. We should research into it more. We should jot it down on the list, the map. We should do our best to map these and then model their dynamic evolution going forward. So this Mercury Cazimi is happening right now, and we do have a coronal hole high-speed stream impact coming up. It's expected on the 15th, so we can give that a watch. We can see this coronal hole here, and this is our 193 angstrom imagery. This coronal hole we've been watching many times. It's been on the sun for a long time now. It's perfectly correlated with all the high magnitude earthquakes that we've had over the past 6 months or so. Right now, earthquake activity is quite low, and I could see us having a big magnitude 7 quake pop off anytime in the next few days. I would not be surprised. Like, I think we'll get one before the 20th of May, but we're not in that high-speed stream yet. But earthquake activity at a global scale in terms of the magnitude 5 rhythms and everything isn't showing that there's like a kind of like an excess of energy already that is needing expression, if that makes sense. But we do see very well correlated time and time again with this specific coronal hole and many others, but this one specifically, because it's cutting through the equator, it's wide, it's a negative polarity, all the attributes they need for that high-speed stream to connect well to the Earth, for us to be embedded within it for a long time. That seems to have a strong influence over global seismic activity, especially with these high-magnitude earthquakes. So that high-speed stream structure is expected to come in around the 15th, and then there was also a shock wave from the 5.7 M-class flare and coronal mass ejection that was launched out a few days ago. That's expected to be combining with that co-rotation region. And the original estimate for this storm was a G1. Now NOAA's published an update that G2 storming should be expected from this. So we do have a geomagnetic storm coming in over the next few days, and that will be driving more aurora than normal, you know, energizing the Earth a bit more than normal. These are the sort of things that, you know, help along seismic activity. And also, we've been having all this crazy volcanic activity. Deep sea volcano erupting in the central Bismarck Sea in north of Papua New Guinea and around those islands. It's quite bizarre. Kilauea volcano is looking like it's about to erupt with its 47th episode. So there's a lot happening already. We have this sunspot group right here. It has grown tremendously over the past week. It's now a pretty big sunspot, like almost like it's like a mega sunspot. If it blasts off from the limb, it could trigger a proton radiation storm. We got this guy. It could pop off at any moment. You see there's a bit of activity there. It has done multiple M-class flares and X-class flares, but it's been quiet for the past few days. But I wouldn't be surprised if it's just like waiting for the perfect Earth alignment and then boom shakalaka happens. Because keep in mind, this Mercury Cazimi really goes exact tomorrow. Well, guess where that guy is going to be? It's going to be here tomorrow. So again, it'll be Ceres, Mercury, Sun, this sunspot, and the Earth in alignment tomorrow. This coronal hole playing into that as well. So this is the critical energy convergence that I've been tracking on the channel, and we are now in that time period window. That list, by the way, that we looked at fairly early on, the asteroid list is at the bottom here. If you go to spaceweather.com, linked in the description, same with the other things I've shown you. You can check out this list. You'll notice that some of these events now are missing because there were some flybys that occurred on the 7th, but in general, as they find them, they update them here. And this is the place to go if you want to keep track of this. And if you watch this, you'll notice that often, very rarely are that many dark orange ones. And look at all the others that are getting close too, right? We're clearly in some like focus region right now. I think that's undeniable, effectively. These sort of data links for tracking the sun and Schumann resonances and global seismic activity, for example, can be found on my website, earthevolution.com/energy-analytics. And if you go to the store here, you'll notice that we have a whole bunch of products that I offer. These are all organic herbal tea blends. We have herbal coffee, really fantastic stuff. We also have merchandise and more. There is a sale going on right now till the 16th. If you did not know, it's all one word, Community 26. So you can get 5% off your order if you pick something up. And everything's in stock. My dad, as many of you know, he went in for heart surgery recently. He's feeling great. Just some very minor things, but overall feeling good. We're not concerned. He's just wanted to let you know that he's doing good. He thanks you for all your warm well wishes. And if you pick something up, he'll ship it out to you pretty quickly. He's also already been back to work, mixing up new tea blends and product and everything. So just again, I was talking to my dad on the phone just like an hour ago, and he said, let everyone know that I'm really appreciative for all the prayers and kind words, and that you know, I want to ship some stuff out to them. So if you want to pick something up at a nice discount, we don't run promotions that often because I offer everything already at fairly, you know, good fair prices. Why do it if, like, I'm not here to be greedy? Community 26, all one word. It's linked in the video description. You can check it out, and we'll get that out to you right away. And we have an in-person community event coming up this Saturday. We're going to be playing the singing bowls. We're going to have a bonfire, qigong. It's going to be really incredible for this energy convergence in San Diego. If you live nearby, you should definitely consider it. And I would highly recommend it. It's going to be a life transformative event. Maybe not for everybody, but certainly for a lot of people. I think it's going to be a life transformative event, all of us coming together. And there are still tickets available, but not that many. So reserve your spot. Maximum attendance is 150. So this is coming up on the 16th, and really looking forward to seeing all of you there who are in attendance. And you can learn more about this by going to the Earth Evolution website. So with that, we will do a question and answer, and then I will be on my merry way. But if you have any questions, please ask them in the chat. If you want your question answered, attach it to a super thanks. I will answer all of them. And yeah, the other last thing I wanted to mention is that we have 5 guest speakers for this event. And I'm pretty sure I'm going to set up my live stream for those guest speakers, so you can watch the guest speaker presentation, because you know, this audience here, all of you are much more international and worldly than many people realize. We have people in every single country on this planet watching this channel. So if you're in Hong Kong or Ethiopia or France, and you were like, hey, I wish I could attend, but I can't, obviously. Well, there'll be a live stream for the guest speaker presentations. And if you are someone that already has product, then that may be something for you to consider, to brew up a cup, for example, of spirituality, and then watch along with the live stream and join in on that collective vibe. So I would definitely recommend that. I think it's going to be a lot of fun. I hope to see you there either in person or for that quick live stream. So if you have questions, please ask them in the chat and I will get to them, and super thanks will all be answered. See, here we have someone from Slovenia. Hello and welcome. Here's a good question from Plant Lady. What if one of those asteroids hit the moon? Well, the moon would take that impact like a champ. It wouldn't be any problem. The thing is, the moon doesn't really have an atmosphere. So here on Earth, we have a thick atmosphere, and these asteroids, often, if they're small enough, burn up in the atmosphere. For the moon, you're getting an impact on the surface. So the interesting thing about the moon as well is that it actually has an orbital inclination. I can perhaps pull up a graphic of the moon really quick. I should have one pretty easy to access, showing the inclination of the moon. Maybe I type in lunar. Let's see what pops up there. Here we go. So here is a graphic that I created for the lunar nodes. And you notice that the moon has an inclination to its orbit. It's actually about 5.15%. So it's not exactly along the ecliptic plane. But if we go back to our asteroid belt, you know, a lot of these asteroids, they're coming in at these angles. So if you have something exactly along the ecliptic plane, the moon can interact with that, the Earth can interact with that, but the Earth is almost exactly along the ecliptic plane. Because again, more evidence for this idea and this theory is that as these things impact, their orbits become more circular, less elliptical, more circular, and the inclination reduces. So that's what we see with Earth and with Venus too. We have near perfectly circular orbits, and the inclination for those two planets is very, very low relative to the ecliptic plane. The moon, though, can kind of swing down, and perhaps it can impact something like an asteroid passing below the Earth. The moon happens to be there because it has this 5.15% inclination. It can get it. So the moon is also working in this accretionary dynamic and is actually absorbing a lot of these impacts as well on these cosmic timescales, which is interesting to consider. So good question. Just looking for another question. I'm looking for questions that are relative, focus on the topic of today's video. That's really kind of the important thing here. And at least with I'm not seeing it, with what I'm scrolling through right now. Here's one. Martina, genification. Is there anywhere on the planet more prone to being impacted by an asteroid? Will you ship to Australia again? I've never shipped to Australia, by the way, for the website. I wish I could. It's just not possible. Is there anywhere on the planet more prone to being impacted by an asteroid? I think the impact chances are all effectively the same. I mean, maybe there's some slight variation, but I don't think so. I think it's basically all fair game. So I can't definitively answer that. It's a good question, but off the top of my head, I don't think there's anything that would seriously impact that. It really depends on these orbits. I guess you're going to get more probably in the equatorial regions because you do have these orbits aligning along the ecliptic plane, but you could have something just barely above the ecliptic plane that still could hit down into the North Pole or Antarctica or something. So I don't think it's probably that big of a deal. And a question here from Dave, which is, isn't this a normal thing? But only the first time someone openly talks about it and explains it all. Yes and no. It is totally a normal thing. Um, there's degrees of normal, okay? In our normal day to day, we don't see this many, like every single day, we don't have this many asteroids coming in this closely. But on a longer time frame, yeah, we do get these sort of convergences frequently, okay? So yeah, it's notable in terms of like right now, it's one of the more notable things happening in our space environment. I would say it's probably the most notable thing happening in our space environment. Um, this asteroid wave that's coming in. But yeah, we've seen things like this before. We will see things like this again. It's good to be aware of that. It's good to have some understanding of it to the best of our ability to try to really piece out, like figure out what the truth is and be ready for perhaps big things to happen, big impacts. That's my thought process there. Mary Prince, thank you for the super thanks. Why watch asteroids coming near Earth, but they have no way to push it away? Will you give us a heads up if something will hit us? Hit us, glad for your dad. Yeah, I mean, we'll probably all find out at the same time if something's going to hit us because it'll probably just hit us. That's the more likely scenario. We are getting these better all-sky surveys, but these asteroids still in general are very dim and dark, and you need to simply catch it at a far enough distance that then you can calculate it and see it's coming in. So these fireball sightings that we've had, for example, in March and in April, right? We're not picking those things up ahead of time. He says, oh, there the thing is raining down and causing sonic booms and flying into houses and stuff. So I'm giving you a heads up right now, the fact that there is an asteroid wave, and it doesn't mean we found every object in this jet stream. It's just evidence that we are in a jet stream. But beyond that, I can't really help you too much. Is there a connection with these asteroids to AMOC slowdown or Earth rotation? With AOMC slowdown, no. That's a circulation of the ocean. I mean, yeah, maybe some giant impact. Obviously, it's going to influence ocean circulation and everything. This is like bad news, like a bad news impact, like a deep impact, one of these movie type impacts. But no, that's different systems. Earth rotation is a little different. In terms of these, let's say even all 8 of these asteroids that we're tracking, 8 or 9, let's say all of them hit Earth, they would all blade into the atmosphere. Would that affect Earth's rotation? No. Now in the past, Earth, the planets got the rotation through a variety of factors, but one of them was the accretion of these planetesimals. You have what's known as the isochronism of spin, where all the planets in general, except Venus, are spinning the same direction. And roughly all in the same time period too. And well, this jet stream accretion, these dynamics, help to explain this isochronism of spin. You also have a transfer of angular momentum from the central body, which is in our solar system, the sun, to the planets via plasma being brought into a state of partial co-rotation around the sun. Because of the magnetic fields, the infalling gas ionizes. We can go back here to see this. The infalling gas ionizes. You have a strong magnetic field. You have rotation of the central body. And so this plasma, we're looking at a cross section here, okay? This plasma is brought into a partial co-rotation around it. And now through the magnetic force, you have the ability for angular momentum to be transferred. So, but that's a long time ago. In terms of these asteroids now influencing Earth rotation, it would have to be some huge, huge, huge impact to do that. These little guys wouldn't do anything. Take maybe a couple more questions. What would have to happen for the asteroids to be intercepted and become a part of Earth's orbit? They just have to cross paths. So if it's getting intercepted, it's now hitting the Earth, the atmosphere, the Earth itself, whatever. So, but just the fact that Earth exists in its orbit, creates this gravitational accumulation point, and then the asteroids themselves, as they interact together across time, will help the orbits become more self-similar. Again, we see that with this graphic that I'll have to pull back up again right here. right here. This one I think is a really beautiful illustration because it really clearly shows this dynamic and process, right? The interactions between these asteroids, these little pieces, bodies, grains, whatever the different sizes are, right, help these orbits become more self-similar across time, and then eventually that will be interacting with the Earth. That's at least what it seems. And the last question I'll take is, what are your thoughts on Apophis? Apophis is a huge asteroid that is coming in. Let's actually pull up the, let's pull it up here. So we'll have to kind of go here and go to our add or remove object. You can only have so many objects here loaded in. I don't know why they put a cap on it, but whatever. Let's type in Apophis. And get this back up for you guys. Okay, it looks like we have it loaded now. And it is also showing us all the old orbits, just FYI. If you're wondering what these other things are, they're all the old orbits. That's how you can keep them in there, but you don't actually see it anymore. But here we see Apophis. If we play forward, eventually in 2029, we will get a very close flyby with Apophis. And let's even speed this up to, say, 3 days. And that's 2028. Let's go forward again. Boom! There it is. Let's go back. And looks like we're going to have to go back a little bit. Ho, ho, whoa. Okay. Look at that. Now, Apophis is big, all right? Look how close Apophis gets. Let's do a 1 hour jump now. It's getting very close to our planet. And this has a lot of people concerned. I certainly am concerned. They've done calculations showing that it should be fine, but hey, you know, I have some reservations, and it's 450 meters by 170 meters in size. So let's average that to 300. That's actually pretty close to the middle. Let's just average that to 300 meters, okay? And let's bump this up. Let's make it an iron meteorite. And let's drop this guy in. And actually maybe, I'm not sure if it's going to tell us its velocity here. Average orbital speed, 30.73 kilometers per second. It's behind me in the video. I'm just looking at it. Or yeah, so let's type in, let's put it at 30 kilometers per second for our asteroid launcher, which actually I don't know the mile per hour conversion for that. We'll drop it in at 45,000 miles per hour. Let's 50,000 miles per hour. Actually, if it's 30, it's going to be more like 70 or something like that. Let's drop it right here. Let's check out Apophis. If it hits, 1.6 mile crater. Crater is basically 2,000 feet deep. Impacted the ground incredibly fast, 102 megatons of TNT, more energy than Krakatoa in 1883, impacted this size every 7,000 years. You have a 236 decibel shock wave. This just destroys buildings, eardrums, lungs, everything. 6,222 mile per hour peak wind speed, and a 5.8 magnitude earthquake. Yeah, so we don't want this to occur, but they have, and they will continue to occur. We can even type in like largest impact craters on Earth, and we will see this map here. And let's see if there's maybe a bigger one. I guess I can just zoom in. It's an SVG file. Okay. Look at the Vredefort impact there, Africa. Diameter 160 kilometers across. Okay. You have Chicxulub, 150 kilometers across. You have down here, I don't know this one. It's actually not letting me select it for some reason. Yeah, the Sudbury, 130 kilometers across. Huge mineral deposits, by the way, in Sudbury. Very interesting. You have some other big impacts here, all across Europe. Of course, think of all the impacts that hit the ocean. Big impacts. They happen, and they're going to continue to happen. That's the thing. So there's always a lot that is happening, and I will keep you up to date on all of it. So thank you all so much for watching. I hope this helped you to learn a little bit more about our space environment, our solar system, the risk of asteroids, some of the physical dynamics taking place in our solar system as it relates to asteroids, and much more. So please stay up to date, subscribe, smash that thumbs up button, help this channel grow. I've been your host, Stefan Burns, geologist, geophysicist, space weather guy, your cosmic bro, here to help you understand what is happening on the planet. Remember, just a reminder that we have our first in-person event on the 16th, this Saturday. Still time to sign up if you live in LA, San Diego, nearby areas. I highly recommend you do so. And also we do have an ongoing sale right now, 5% off on earthevolution.com/store using the code community26, all one word. All the links and info are in the video description. Have a great day. Wishing each and every single one of you well, and I'll see you all in the next video.